we will go on to the next part of circle criterion to see what a circle criterion is. In order to go to that, we need to know a little bit of transformations. So in the last class, what we had seen was that if I am having two passive systems in feedback, for example H1 and H2 in feedback, and if both H1 and H2 are passive, then if this system is also proper and it is controllable and observable, then we can say that this whole system is asymptotically stable. So what did we say? That means if H1 is positive is a strictly positive real function, and also H2 is also a strictly positive real function, then the feedback connection of H1 and H2 will lead to an asymptotically stable system. Okay, asymptotically stable system. If H1 and H2 are passive, or in fact we can call it as positive real functions. Okay, positive real transfer function, positive real transfer functions. Okay, now can we extend it to the nonlinear system? That is what we are going to see. Suppose you are given a g of s here, some nonlinear system here, g of s is nonlinear here, and this too what we were speaking was linear systems, nonlinear system, and I have some feedback k, or k can also be a nonlinear part here. And here if there is a feedback connection between these two, can we use the linear control techniques such as tools such as the Nyquist plot or the Nyquist criteria to assess the stability of the whole system. That is what we are going to see. Okay, so for that, let us initially consider a nonlinear system and see whether we can take the nonlinear part out from it, and then we can do some kind of transformation to assess the stability of the linear part, and then speak about the stability of the whole system. That is what we are going to see. So let us consider an example here, that is d squared y by dt squared plus 2 dy by dt plus 2y plus y cubed equal to 0. Okay, so this I can write it as d squared y by dt squared plus 2 dy by dt plus 2y is equal to minus y cubed. Okay, so here I can write this as equal to, take y minus y cubed as equal to u. So I have taken minus y cubed into a variable u, so that we will not have to deal with this nonlinear part suddenly. Okay, so so that we can take the Laplace transform of this system. Okay, so I get here s square times y of s plus 2 times y of s plus 2 times y of s, oh here there is an s here, is equal to u of s. So this implies that y of s by u of s, which is in fact the transfer function of the system, is equal to 1 by s squared plus 2s plus 2. So here if I put 3, this would be a good system actually. S plus 2, 3, I can take it as 3 also. This is good. Okay, so now how can you draw this? So here I have u of s here, and this is g of s, and this is the y here. I have a u input here. So now what is u actually? U is actually minus y cubed, right? This I can take it as a nonlinearity. U is actually minus y cubed. U is equal to minus y cubed, right? This is what I have. So this I can take it as a nonlinear part from this. This is in fact a nonlinearity taken back from here. This is a nonlinearity which has been taken to u, right? This is actually u. This is minus y cubed has been taken as u. So here I can put this is right. Okay, this. So this is actually cube of this part into the whole power 3. Okay, so where do you, if you look at y cubed, if I have the input as y, and y cubed will be something like, sorry, it will be something like this. Y cubed would be something like this, right? So this part, if you look at this part, we can see that this function is on the first quadrant and on the third quadrant, which shows that this is a passive system. Okay, lying in the sector 0 to infinity. This is a passive system which lies within the sector 0 to infinity, showing that this nonlinearity that we have acquired to U is a passive system. Okay, and now how can we check the stability of the whole system? If, since this is passive, and if GS is also positive real, then we can say that even though we have a nonlinearity here, we can say that the whole system is asymptotically stable. So what we have to do is we have to go and check the go and look at the Nyquist plot of GS, and then we can say that if it is on the right half of the imaginary Gj omega axis, then we can say that G of S is strictly positive real, and then we can say that even though we have a nonlinearity of minus y cubed here, the whole system is asymptotically stable because this term here is passive here and it lies within 0 to infinity sector. Okay, so that is the idea that we are going to use for the rest of the systems. Okay, for analyzing the stability of the nonlinear systems using the Nyquist plot. Okay, now suppose we have something of the sort here. One second. Okay, so now if I have some nonlinearity of this form, for example, I have some kind of a nonlinearity. For example, you know the saturation kind of nonlinearity, it is something like this. So this kind of a nonlinearity, I can say that this nonlinearity lies within this sector, right? Sorry, does not lie between this 0 to infinity sector, that means 0 slope and infinity slope sector. This lies within, that means there is a bound for this. Let me call this bound as some K2. It lies within some sector 0 to K2 sector. Okay, so I can say that I can also bring the nonlinearity within some sectors. So we want to see what all transfer functions G of S can be what all plans can be connected to this kind of a nonlinearity so that the whole system remains stable. Okay, so let me consider a system which has a feedback nonlinearity. This is, I am going to look at systems with a feedback nonlinearity of this form. So I have some kind of a nonlinearity like this. So this is y and this is f of y, the output of the nonlinearity. So here, and this lies within some sectors, two sectors. That means this nonlinearity lies within some sectors K1 and K2. K1 and K2. Okay, so if our GS, I have a GS here, and we have the nonlinearity here, and it is being fed back here as u here, this is y here, this is negative. So let me call this as, when it come to the nonlinearity, let me call this as zeta and this as f zeta, so that we can say that the input to the nonlinearity is zeta, which is taken from y, and the output of the nonlinearity of f zeta, let me call it as the nonlinearity, let me call it as phi of t comma zeta, y is equal to zeta here. Okay, so now what happens here? Like we think that since this nonlinearity lies within this K1 and K2, where K1 is the slope of this line and K2 is the slope of this line, we can have an intuition, we can have a feel that this whole system can, for any values of k between k1 and k2, the whole system might be asymptotically stable. That means if I choose some k within k1 and k2 and plug in instead of this nonlinearity, so we expect that this nonlinearity can have a maximum slope k1 and maximum slope k2. So with that assumption in mind, we may think that this whole system can be stable for any values between k1 and k2. Okay, so but this was in fact Eiserman's conjecture, but this was proved wrong using a counter example at a later stage. So now, so since this cannot be true, we have to go and see what are the conditions or what are the plans that can be stable for if I have a nonlinearity lying between two sectors k1 and k2. So when I write sectors k1 and k2, this is represented as M lying M k1, sorry, this is a closed M k1 comma k2. That means this psi of t comma zeta is an element of M k1 k2. If how do we write here? In this case, if this is psi of t comma zeta, this is some other nonlinearity, I can write here psi of t comma zeta is an element of the sector 0 comma k2. Okay, so I can have another sector like this, something like this. So I have a nonlinearity like this, and I have a sector here. This is k1. So this sector we can write it as psi of t comma zeta is an element of the sector k1 to infinity. K1 to infinity. Okay, so now how let us see how we can transform. We know that this nonlinearity, if it lies within the sector 0 to infinity, the whole this system is passive. This nonlinearity is a passive nonlinearity. So, and we have checked for a passive nonlinearity, if GS is also, if I have a passive nonlinearity here and if GS is also passive, the system is asymptotically stable. So now if you are given some nonlinearity within some sectors, we will try to transform it to the 0 infinity sector and find the values of what all values of k1 and k2 and what all values of k, the system is asymptotically stable. So let us start with we will start with this kind of sector here, and we will go forward and see what happens to the system. Okay, so first let us suppose that psi dot is an element of this sector k1 comma infinity. Okay, so I have this here, so I have this part here, so I have it here and then I can bring it here. So this is okay, I will do it in a different form. Okay, it's better to draw it. So here I have it like this. This is like this. This is a nonlinearity here, and I have my sector is somewhere here. Okay, and this is my sector here. This is k1. This nonlinearity lies between k1 to infinity. Okay, so this is zeta and this is f zeta, which I can call it as xi. Some xi, f zeta is equal to xi. So I give an input zeta to the system, I get the output as xi. Okay, so now what we are going to see is we have to shift this k to the 0 and make this nonlinearity to the sector. We have to make this nonlinearity to the sector m0 to infinity sector. That means I have to push this k1 down to this line and move it to m0 to infinity sector and say that this whole system, whole nonlinearity is passive in the sector 0 to infinity, and we will find the values of G, values of plans for which this whole system is asymptotically stable. Okay, So how do we convert to the M0 infinity sector? So for converting it, let us see this distance. That means this is xi of t comma, this value is xi of t comma zeta, tie of t comma zeta. At any point at zeta here, what is the value at this point here? At k1, it is k1 times zeta here. This is a slope k1. This red line is a slope of some linear plan here. So what is the value of this plan? That is k1 times zeta here. And what is the value of this point here? It is xi of t comma zeta. So what is the difference here? This is xi of t comma zeta minus k1 of zeta. It will always be positive here. And here also, if I take the difference here, that is here xi of t comma zeta minus k1 into zeta. Here this will be, here both will be negative, and here also this difference will be positive. So I can say that this psi of t comma zeta minus k1 times zeta, the whole transpose into zeta, is always greater than 0. In here also if we take the difference, here also if we take the difference and then multiply with zeta, here zeta is positive and here zeta is negative here, and here I get minus, here what is the value? For example, here it is minus 4 and here it is minus 2 here. So minus 4 minus 2, minus of minus 2, it is negative, into a negative value is positive. Here I get a positive value into a positive value is positive. So this term is always positive. That means this part, this, if I have a nonlinearity of this form, then if I have an input of zeta and an output of xi of t comma zeta minus k1 zeta, then this function, what is this, is always positive here, and therefore this system is a passive system. If this nonlinearity, if I have a nonlinearity of this kind of a nonlinearity is a passive nonlinearity. So if I have something like this, if I have, the initial system was like this, I had an input nonlinearity zeta here, and this was a nonlinearity here, and I got xi was the output here, xi of t comma zeta was the output, and this was fed to what I say here, the initial system. The actual system was like this, I have a GS here, the input is u, when I give input u to GS, I got the output y, and y is fed back to the nonlinearity, and y actually is zeta here, and here I have a nonlinearity here, I get the output as xi here, and xi is fed back here, and I have it is negative here, so u is equal to minus xi. This is our actual system. So now here this nonlinearity has been is being converted to M0 infinity sector. Okay, so now the input, when I try to convert from K1, when I try to shift K1 to the 0 line, what happens? I get some relation like this, and for this kind of a relation we can consider zeta as the input and this as the output. And since this is always greater than 0, so for this new nonlinearity, we can say that this new nonlinearity is asymptotic, is passive. Okay, and this new nonlinearity lies within the sector 0 infinity. So I can write here, I have some zeta here and some output here as xi of new output I got here, xi of t comma zeta minus k1 of zeta, right, k1 zeta. This is a new nonlinearity here. So I will get, I should have a new block here, right, I should have a new nonlinearity here, new block, new system here, which transforms zeta to this part. Okay, new NL1. So I have a new nonlinearity here. So what should be that nonlinearity? So that this is phi of t comma zeta minus k1 zeta. So we will see what that will be. Okay, so I have the input as zeta. If I have the input as zeta and I have the output as what is it? One second, output as, I'll move a little bit to this left, xi of t comma zeta minus k1 of zeta. So if I give, I should use actual nonlinearity and add or subtract some terms so that I should get something like this. Okay, so here if I put the input zeta to the actual nonlinearity, what would be the output? I get here as xi, right? I get the output as xi of t comma zeta, xi of t comma zeta. So what is it? I want this output here. I want a new nonlinearity which gives this output. So I want a new nonlinearity which gives this output here. I want a new nonlinearity here. That is, when I give an input to this nonlinearity as zeta, this new nonlinearity as zeta, I should get an output here. So what should be connected in between here? So in order to get psi t comma xi minus k1 zeta, what should I do? I should put a feed forward here, right? Feed forward here using a negative feed forward here. So I have here, if I put through k1 here, I put a k1 here and I try to subtract phi of t comma zeta minus k1 into zeta. What would be the output? I get phi of t comma zeta minus k1 into zeta. I got this new nonlinearity NL1, right? NL1. Okay, so now I have psi tilde. Let me call this as psi tilde. This is, I have given it as phi tilde. Let me call this as psi tilde. This is psi tilde actually. This is psi tilde. Psi tilde transpose into zeta is greater than or equal to 0. So this is passive. This nonlinearity 1 is passive. So what happens to the actual system now? What happens to the actual system now? I have an input here. I have changed the nonlinearity, actual nonlinearity to nonlinearity 1. So now I have the output here is y for the system is constant. So because the input to this new nonlinearity zeta itself, so I have the zeta coming out of here as y equal to zeta is equal to y. It goes to this new nonlinearity. So I am not drawing this block here. So I will draw this as NL1, new nonlinearity here, NL1. And what is the output here? Xi tilde, which is equal to xi minus k1 zeta. Okay, so now when I try to feedback this to this actual system, what is my new u? I get a new u here, right? This is negative. So my u is nothing but it is a new u, that is u tilde. Let me call it as u tilde is equal to psi tilde. So when I try to give u tilde to this g of s, when I give u to g of s, the output is actually y. Okay, I should get an output y so as to feed to this nonlinearity 1. So what should be the transfer function here so that I should get an output y? Okay, so output y here. So when I give u to g of s, I get an output y. So but what should be given when I give u tilde to some g, let me call it as g1, I should get an output y, the same output y. Okay, so what should be this g1? Okay, so let us see what is g. G is nothing but, g of s is nothing but, this implies here I have g of s is equal to y by u, or what is u here? Y by minus zeta here. Okay, y by minus zeta. Minus, not minus zeta, y by minus psi. Y by minus psi, or it is zeta by minus psi. Y is zeta and u is minus psi. Okay, u is minus psi. Here actually u is minus psi. Okay, now let us see what happens here. So I want the output as y, that means g1 is, new g1 is y by u tilde. Okay, so that is zeta by, what is u tilde? U tilde is, what is u tilde here? Here what is u tilde? Okay, xi minus k1 psi. Xi minus k1 and zeta, k1 zeta. Xi minus k1 zeta. Let me try to divide numerator and denominator by minus xi. So this will lead to zeta by minus psi divided by this by minus psi is equal to zeta by minus psi is equal to, okay, this is my by minus psi is equal to, this is minus, okay, here it is actually u tilde is equal to minus of this, right? Okay, I forgot, u tilde is equal to minus of psi tilde. U tilde is equal to minus of psi tilde. This is actually not psi tilde, it is minus of psi tilde. I did a mistake here. So u tilde is coming here as minus of psi tilde, which is equal to minus of psi tilde here. So this divided by minus of minus psi tilde by psi minus psi, this would be 1, and minus of minus is plus 1 plus k1 by zeta by minus tilde is plus k1 into zeta by minus psi. So zeta by minus psi, what is zeta by minus psi? It is g of s. So I get this as g of s divided by 1 plus k1 into g of s. Okay, so this is what is happening here. So how do I rearrange the system? So I have this minus psi tilde here, and for this system, in order to get the actual y here, if I had the input, if I had gs here, gs is system that we have, then this is u, right? This is u that I have. If u is given to gs, I should get a y. If u is given to gs, I should definitely get a y. But what happens here? Here the actual input is psi tilde, minus psi tilde. Okay, so now here what we can do is we can give a feedback here. What is the actual system? gs divided by 1 plus k1 into gs. So it is actually a negative feedback here. I can give it using a feedback here, minus k1 here. This is the feedback that we can give here. Feedback here. So I have a feedback here which gives the new system here. This is g1 of s. So now what we can say that if I have a new nonlinearity psi tilde here, then if I have a nonlinearity within the sector k1 to infinity, then I can convert it into the sector 0 to infinity, so that my gs changes to g1s. So in this form, g1s of this form, gs divided by 1 plus k1 into gs. So now what is the idea here? For this nonlinear system to be stable, to be asymptotically stable, what happens? We have to go and check whether this gs by 1 plus k1 into gs is positive, real or not. So we have to check for g of s divided by 1 plus k1 into g of s is positive or strictly positive, real or not, for asymptotic stability, real or not. Okay, so this is what if I have a nonlinearity in this sector. Now suppose if I have a nonlinearity in another sector, suppose we can go to another sector, that means I am having a nonlinearity within the 0 to k2 sector, another sector. This I have already done here, so that in a similar way we can proceed. The previous one we had seen, that means psi lying between k1 and infinity sector, and we saw that if this lies within k1 and infinity sector, we should go and check the positive realness of gs divided by 1 plus k1 into gs. Okay, then if this is positive real, then we can say that this whole nonlinear system is asymptotically stable. Okay, asymptotically stable. Now if we have the nonlinearity lying in another sector 0 to k2 sector, here also I have the same, we will do the same procedure here. Here now if I want to convert it to the sector 0 to infinity, first we have to convert it to the sector 0 to infinity, so that the whole system is passive within this interval 0 to infinity, and then we have to find a new g of s which satisfies this condition, new g of s which can be used in the whole system. And then we have to go and check the check whether this new g of s is positive real or not. Okay, in that case also we can here what the difference is, k2 into xi minus xi transpose into psi is positive. We are subtracting in the reverse order. In the previous one we had subtracted in the reverse as xi minus k1 into zeta. For that was the difference here. So here what we are going to do is, instead of changing in the first system, what we had done is we had kept the input to the nonlinearity constant and the output we had made it as psi tilde. For the second case, what we will do is we will keep the input as k2 zeta minus xi and the output as xi as a constant here, psi as a previous thing. So what changes has to be done to the nonlinearity here? So in order to make that correct, so if I want an input k2 zeta minus xi and the output is zeta, if the input to the actual nonlinearity is zeta, the output was psi. So this much part you know. Now if I want the input as k2 xi minus zeta, so what should be, this is the line is going like this. So k2 zeta into 1 by k2 is zeta. So I have this part as k2 zeta and I have to subtract k2 zeta minus psi. So I take psi from here and subtract it and I give it as an input here. So this is the modified system here, modified nonlinear system here. So when I modify this nonlinear system like this, what will I get? What should be the new G2 of S? I should get a new G2 of S which satisfies this nonlinearity. So I have the input as xi of t comma zeta itself, but the output has to that nonlinearity from this new system has to be different, so that the whole system is the same. Okay, so I have k2 xi minus zeta here. So when I have k2 xi minus zeta here, this is minus I, the output should be k2 zeta minus I. So I should have a new G2. In order to have a new G2, what should I have? We just multiply it. G2 minus I into G2 S is equal to k2 into xi minus I. So what should be G2 of S? G2 of S is equal to k2 into xi by zeta minus xi by zeta plus 1. So divide it by minus xi. So I will get it as k2 into gs plus 1. Okay, k2 into gs plus 1. It is minus zeta by psi is gs plus 1. So how do I draw it? I have gs here. I should multiply gs with k2. Here I got here k2 into zeta here. Then I get this psi over here. Okay, xi over here, that is what I get it here. Okay, so here I connect, actually this is minus here, this is not plus, okay, plus 1. Okay, k2 into zeta plus 1, this is minus 1 here, so it is actually k2 zeta minus xi. Okay, it is coming here as k2 zeta minus xi. So now what we have to do, we have to check whether G2 of S is a positive real transfer function or not, in order to see whether this whole system lying within the sector K2 and 0 is asymptotically stable. Okay, since this nonlinearity, this new nonlinearity what we got here is passive, what we got here, this is passive, Then if G2 of S is positive real, then the whole system is asymptotically stable. Okay, so we got for this sector. Now we have the next one, which is lying between K1 and K2. K1 and K2, K1 and K2. So in order to see for K1 and K2, first what we do is we will first shift this axis, this xi comma t comma zeta to K1. First we will shift to K1, shift it to K1, and then see whether, so I will have this xi of t comma zeta and shift it to K1 to infinity. Check for the K1 to infinity sector, and then in order to move from K1 to infinity sector, what changes I have to make? I have to make it as G1s. G1s is equal to Gs divided by 1 plus K1 into Gs. The first change that I have to make is on this non-linearity one, using this K1. So I get Gs divided by 1 plus K1 into G1s. Okay, so now what I have done, I have shifted this zeta to this K1 using this transformation. So I got a new non-linearity like this. I got a new form like this. It would be something like this. I have K2 is already here. I didn't do any changes in K2. I had only K1 here. I assumed that K1 was only there. So I shifted xi of t comma zeta to K1, moved K1 down so that xi of t comma zeta shifted to K1. So I have here as xi of t comma zeta here. So this is actually new. This is our psi tilde here. Okay, xi tilde here. So now I have a new nonlinearity xi tilde lying within the sector K2 and 0. K2 and 0, that is our second part that we had done, lying within the sector K2 and 0 with a change in Gs as G1 of S. Gs has changed as G1 of S, that is Gs divided by 1 plus K1 Gs. Okay. So I have this Gs here. And with this new Gs and this new nonlinearity, I have to shift this K2 to 0 to 0 to this is K2 to 0. Okay, it was 0 to K2. 0 to K2. It is actually 0 to K2. 0 to K2 to the 0 to infinity sector. Okay, 0 to infinity sector. Okay. So that is what we have to do here. In order to move it to 0 to infinity sector, this already have to, when I shift this xi to psi tilde to K1, that means I have already one K1 here, already shifted K1 here. So I get a new K here, that is K2 minus K1 here. So the new nonlinearity, new transformation, loop transformation would be, in this G1 of S, you have to get the new G2 of S. Okay, I already have a G1 of S. With that, you have to add this K here. Okay, why does this K come here? K is, that means I have to shift this K1. That means I am already having this shifted one as psi tilde minus K1 of zeta. And then if I want to shift it again, if I want to shift it again, that means I have to shift again by K1. Again by K1 here. So I have this K2 minus K1 here as K. So I will get a new K as K2 minus K1 here. So that is what, that is the difference here. So now here I have this new nonlinearity with this new K, and this part, this whole system has been shifted here with G as G1s and this NL as NL1 and K2 as K1. That is the only difference here, K2 as K. Okay, so now what will be the actual system? This is the actual system actually. This is the actual system. So we have to find out this G2s. What is G2s? That is 1 plus K into G1s. So what is G2s? 1 plus K into G1s. So what is G1s? G1s is Gs divided by 1 plus K1 into Gs. Gs divided by 1 plus K1 into Gs. So I cross multiply it, 1 plus K1 into Gs plus K into Gs divided by 1 plus K1 into Gs. So what you have to substitute K as K2 minus K1. So when we substitute K2 minus K1, this K1 into GS and minus K1 into GS gets cancelled, and we will end up with this transfer function, that is G2 of S is this. That means if we have a nonlinearity lying within the sector, so here lying within the sector K1 and K2, what happens is that I have this shifting K2 minus K1. So in order to shift this K2 to infinity and K1 to 0 and move this whole nonlinearity, we keep this nonlinearity within the 0 to infinity sector, we made two transformations. First we moved K1 and then we moved K2, and including after moving both these two together, we have ended up with a new transfer function G2 of S, so that I have this G2 of S with this new nonlinearity here, nonlinearity 2 here, which comes here. Okay, so that what would be G2 of S here? 1 plus K2 into GS divided by 1 plus K1 into GS. Okay, so now if I have this kind of a nonlinearity, I should go and check the positive realness of this part, and check see whether this is positive real or not, positive real transfer function or not, and whether this is stable. This is what we have to do to check the stability of the whole system. Okay, so let us summarize this using this absolute stability terms. If I have some kind of a system like this, x dot is equal to ax plus bu plus y is equal to cx plus du, that is what this G of S is, the actual system. I have G of S connected to a nonlinearity NL, some nonlinearity NL here, where this u is equal to minus xi. Here this is psi, this is y is zeta here. This is if I am having this kind of a system. This GS has very nice properties, that GS is actually controllable and it is also observable. Okay, so that I can do any I can define any controllability metrics or any control action for the system. Okay, so now this nonlinearity can be of any of this form. It can lie within the m is equal to 0 to infinity sector, and it can lie within K1 to infinity sector, 0 to K2 sector, or K1 to K2 sector. Can be in any of these sectors. Okay, and if it is in 0 to infinity sector, I can say that psi transpose, this is psi input, xi transpose into xi of t comma xi is greater than or equal to 0. And if it is in K1 and infinity sector, I have xi transpose into phi of t minus xi minus K1 into zeta greater than or equal to 0. This is the passivity condition for this kind of a nonlinearity. And for this kind of a nonlinearity, the passivity function will be of this form: xi transpose into K2 xi minus xi of t comma zeta. If it is in the M1 K1 to K2 sector, what happens? I have this term and this term multiplied together. Here I have given less than or equal to 0 because I have taken the reverse of that, xi of t comma xi minus K2 xi here. So which would be negative here. So that is why I have given a negative less than 0. So I wanted to make this look alike. Okay, so this is less than or equal to 0. So these are the different types of sectors, nonlinearities that can be connected to this G of S. Okay, so if these kinds of nonlinearities are connected to the system, so when can the absolute stability be defined for the system? So we have this theorem which is based upon these loop transformations that we had done just now. So if I have this system and if xi lies within the sector 0 to infinity, we have to go and check the positive real, check whether GS is positive real or not. Okay, if xi lies within this sector, we have to check whether gs by 1 plus I plus k1 into gs is strictly positive real or not. And if xi lies within this sector, we have to check whether I plus k2 into gs is strictly positive or not. And if xi lies within this sector and with k is equal to k1 k2, we have to check the positive realness of this function. Okay, and this theorem is in fact called as a multivariable circle criterion. This is called as multivariable here because I have that means here I have put here as I here, not as 1 here. That means this is not a this is a multi-input multi-output system. Okay, this u is not 1 and y is also not 1. So okay, so the order of u and y is not 1. So it is a multi-input multi-output system, so that is why it is called a multivariable circle criterion. But we will be discussing on having on SISO systems. Okay, single input single output systems, mainly with single input single output systems. Okay, so now we will summarize it as check whether this theorem is true or not using the Kalman-Yakubich Popov lemma that we had seen in the previous case, and using the Lyapunov function here. So using this KYP lemma, we have these terms here, these relations here. This might look difficult. It is not difficult. Only thing is that you have to remember these relations here and use V dot. V dot we know half of x transpose px. We take the derivative of V dot here and then x transpose p into x dot is and half into x dot transpose into px. So we get this, we get it in this form. Substitute x dot here, x dot is equal to a into x plus b into u. So we get it in this form. Instead of pa plus a transpose p, you substitute this part here and this goes here. Instead of pb, you substitute this part here. Okay, then you expand it. So I get it as minus L transpose L minus epsilon p, and here minus x transpose c into u minus x transpose L transpose w here, and here instead of c x transpose c transpose, you do a little more changes here. Y is equal to cx plus du. So instead of x transpose c transpose, you substitute y transpose minus u transpose d transpose here. So here when you substitute that y transpose into u, here you have y transpose into u transpose into d transpose into u. Okay, here you have u transpose into d transpose into u, and one more substitution you make instead of this d transpose, because in order to get to a very nice form like this, you have to make this half of d plus d transpose in this form, and then you will get everything of this beautiful form. So this you can say, because u I don't know whether it is positive definite or not, so and that is why this condition is given here. Okay, this is actually x transpose w, this is w, this is w, sorry, this is w, L transpose w. Okay, so this in fact this is x transpose, kind of x transpose into Lx plus w the whole into this. So this is always positive definite, so this term is negative definite. So this term is also negative definite because epsilon is greater than 0, p is greater than or equal to greater than 0. So the last thing that we have to do here is y transpose u. So y transpose I know it is zeta and u is minus I. So here the only plus sign was here, so u is minus I, so y transpose into minus I into t comma y. So this is using this sector transformation and all, we can see that this is a passive system. This is always greater than 0. So y transpose and xi of t comma y is always greater than 0. So this is passive. So this term is also negative. So we have a negative definite system which is asymptotically stable. So that is about this much the proof of this theorem. which is in fact the theorem on circle criterion. So in fact this is a bit lengthy, but I will just summarize it and say here that that means if I have a nonlinearity psi of t comma zeta lying within the sector M k1 k2, I have taken only this one, lying within the sector k1 k2, we should go and check the positive whether G2Fs is equal to 1 plus k2 into Gs divided by 1 plus k1 into Gs. We should go and check whether this is positive real transfer function or not. Positive real transfer function or not. Okay, for checking the asymptotic stability of the whole system. Okay, so if you have a GS like this and a nonlinearity NL lying within this sector K1 and K2, we have to go and check whether 1 plus K2 into Gs by 1 plus K1 into Gs is a positive real transfer function or not. So how do we check it? We have G of S here. We have to go and draw the Nyquist plot of this function and then check the positive realness of this. So we have to go and check the Nyquist plot of G2S and see whether it lies in the positive real part. Now the question is, can we use the same transfer function G of S? Can we use G of S itself? For example, if G of S is equal to 1 by S plus 1, or G of S is equal to S plus 1 by S plus 2, something of this sort. Can we use G of S, the Nyquist plot of G of S, to check the stability of this system, where the nonlinearity lies within the sector K1 and K2? That is what we are going to see as the main part of circle criterion. So that is how this can be modified as a circle criterion. This function can be modified into this criterion called as circle criterion, which we will see in the next class. Okay. So this is about loop transformations. So I don't want you to get scared seeing all these transformations. Here the only thing that we had been trying to say is that if I have G of S and a nonlinearity here, I have to convert it into a nonlinearity within the sector 0 to infinity. In order to convert it into the sector 0 to infinity, what should be the changes in G of S, so that the whole what should be the changes in G of S, and what should we check to see whether the whole system is asymptotically stable, is what we had been seeing here. So we did all the transformations here and saw the conditions for checking the stability of the closed loop system. Okay, so in the next class we will see with the same GS can we check the stability of the whole system. That is what we are going to see using circle criterion. Okay, thank you.